Right, yeah. In my spaceship.
I don't know.
Okay. This topic does not really fit in anywhere. Like, there's no chapter or section in the book. However, it is a very popular kind of topic to run across on the AP test, be it in a free response question, sometimes in multiple choice. So we're going to go over it right now. All right, and it kind of fits in where where we are right now because it has to do with integration, but definite integrals, right, and also kind of like using graphs and things. So it'll be a good kind of review of those topics. All right, so we call this function defined by an integral because our function, capital F, is equal to an integral from -1 to x. So our variable here is in the limits of integration. Okay, it's right there where x is. So that's kind of a unique situation. All right. You see a lowercase f here. All right. So that's whatever this function is, and the graph of this lowercase f is right over here in our picture. All right. So when we talk about capital F, it's not this. This is not the graph of capital F. This is the graph of lowercase f. To find capital F, what do we do to this thing? Integrate it from -1 to whatever x value we might have. All right. So there it is. So anyway, we're going to complete the table of values for capital F here is our goal. All right. So let's take a look. So if x is equal to -1, we want to find capital F of x. Well, -1 plugged in here, right? Capital F of -1 is going to be the integral from -1 to -1. Right away, without regard to what this is, what's the integral of -1 from -1 to -1 of something? It's a 0, right? Good. That should be an easy one. So boom, it's 0. Okay, got it. So now let's look at the next one here. The next one we're asked to do x equals 0, and so that's the integral from -1 to 0 of our little f here. Well, how can we go about finding that integral value when we don't have an actual function for little f?
Geometry.
Yeah, we're going to use geometry. We're going to use area under the curve. Remember, that's one of the definitions, or one of the ways we can conceptualize integration of a function is it's the area under that curve from -1 to 0. So what kind of shape do we have here from -1 to 0? It's a trapezoid with a height of 1 and base of 1 and 2. All right. So let's see here. It's going to be then, I'll just kind of do the, so it'll be 1/2 base 1, which is 1, plus base 2, which is 2, times the height of 1. And so that gives us, let's see, 3/2. So the value here is 3/2. Okay? That's that. All right, go ahead, fill out the rest of that table. Fill out the rest of that table.
Okay, Ryan.
Okay. So I've started to fill in the table there for the values, so you can kind of check to see what you've gotten so far. Okay. When we look at this graph here, okay, lowercase f, how can we maybe think of it in relation to capital F? What is this a graph of? Besides lowercase f, we can also think of it as a graph of what? The derivative of what? Of big F, of capital F, exactly right. So this kind of harkens back to stuff that we've done before. Remember when we would do problems that gave us the graph of the derivative of a function and ask us to come up with information about the original function. Here we're kind of doing something similar, except now that we have integrals, we kind of expanded what we're able to do here. All right, so looking at this, all right, we're able to come up with our values. Any questions on how we got any of these values here? Okay. Why did capital F seem to increase, and then decrease here from 3 to 4? What happened? The graph of little f becomes negative, which would then indicate, again, with that idea of little f being like the derivative, right, that would indicate that capital F should be decreasing, right, because we have a negative area here, which would then result in capital F decreasing, and sure enough, we see that decrease. Increase because the little f, like the derivative, it's positive, and so that it results in an increase in capital F, and then we see a decrease occur there, as a net decrease there from 4, okay? So now I'm asking you to sketch a graph of capital F. All right, in fact, I'm going to do that over here on this graph. I might get a little confused, but hopefully I might get a little confused. No, it might look a little confused. We'll see here. I'm going to try with a different color. All right, so capital F has coordinates 0 at x-coordinate -1. So -1 is 0, so it starts out right there. Right? And at 0, we're at 3 halves. So 3 halves is like 1.5, so it's going to go like right about there maybe. And then 1, 4. 2, 6.25. 3, 7. And then 4, 6.25. And again, I'm not going to like worry too much about making it like smooth curve. I mean, you can if you want. I guess I will do it. Never mind. I just said that I wouldn't, and I'm doing it right now. Okay, there it is. So there's what maybe a potential graph of capital F of x looks like. Okay. Notice again, we kind of see those behaviors in there of capital F as if f, lowercase f, is its derivative. All right. Remember one thing we know in our first derivative, wherever we have a relative maximum or relative minimum in our first derivative, how does that show up in the original function? As a what? This is a pretty tricky one. Point of inflection. So yeah, if you look here, inflection, right, is kind of changing. We have kind of a concave up going on right here, and then it changes to a concave down behavior right here. And again, that's right at that maximum there. Okay. So there you go. All right, so where is capital F increasing? For what intervals is capital F increasing?
-1 to 3.
Okay, so capital F is increasing from -1 to 3, or I'm just going to say on the interval there, -1 to 3, because, and what could be our reasoning here? Lowercase f is what? Yeah, I'm going to say something like this, because capital F prime of x equal to f of x, right? Capital F prime equal to f of x, these two things, is positive, okay, on that interval.
Let's talk about extrema at all critical points. No.
Could we? I mean, we could.
Do we have to? No.
No. No, not necessary for here,
Okay.
because we're going to ask about it, okay? So, it's very similar to how we described things in the past, right? Before, when we were given a graph of f prime, we were told, okay, where is f increasing? Well, you wanted to see when f prime was positive, all right? Here, in this sense, it's a similar idea, but we just want to make sure we're identifying that capital F prime, which is equal to f of x, is positive on that interval. This is an important kind of like relationship you want to point out here. Just saying because f of x is positive is not quite enough. You need to really connect it back to capital F. So saying this, capital F prime, which is equal to f of x, is positive on that interval. Therefore, the function capital F is increasing on that interval. Okay? Questions on any of that? All right. Let's continue on then. So let's look at number 2. So number 2. Let capital A of x equal the integral from -3 to x of f of t dt for -3 less than or equal to x less than or equal to 4, where capital lowercase f is graphed. Okay, so again, this is a graph of f. Okay, it's f. So which is larger, a of -1 or a of 1? What do you all think here? Take a minute. Think about that here. Capital A is defined as the integral from -3 to x of f of t. So which value will be larger? A of -1, that is the integral from -3 to -1 of f, or a of 1, the integral, which is the integral from -3 to 1 of f. Which one's going to be larger? So Ryan, what do you say?
A of 1.
A of 1, okay. And so what would your reasoning be?
Because so this graph that is shown is the derivative of a of x.
Okay.
A of 1, there's a relative there will be a relative maximum on the graph of a of x.
Okay.
And so there's that. And then a of -1 is coming off of and from a of 1 to, or from a of -1 to a of 1, the graph is increasing.
Okay, so there'll be more a larger value, or whatever. Okay, because between -1 and 1, f is positive, therefore a will be increasing, so it's still going to go up in value. Okay, that works. That's one way to say it. Anyone have an alternative? Yep, Brandon.
I'm going to say if you choose a and -1, you'll only have the area under the curve from -3 to -1. But if you choose 1, you have all the positive area on the graph.
Okay.
It'll be a greater number.
Right, and so both of those ways of saying things are absolutely accurate. There's two different ways to kind of go about it, okay? Ryan chose to go with the idea of f being the derivative, and so therefore using the fact that we can then describe the original function a from the derivative. Brandon went from the other direction and said, okay, a is an integral, and so we're going to talk about the area. Either way is acceptable. I'm going to go, because we're talking about integration and stuff like that right now, I'm going to use the area argument, but what Ryan's argument was just as legitimate, so I'll say it that way. So we're going to say a of 1 is larger, okay, because, okay, more area is accumulated for -3 less than or equal to x less than or equal to 1 than for -3 less than or equal to x less than or equal to -1. Okay, we get more positive areas, what like Brandon said. We get more area, more positive area there. All right, so Connor, how about letter B then? So which would you think be larger here, Connor? Would A of 2 be larger, or would A of 4 be a larger value?
A of 2.
A of 2, okay, why do you say that?
Because A of 2, it gets all the positive area from -3 to 1.
Mm-hmm.
And only a little bit of negative from 1 to 2.
Correct, okay.
But for A4, it gets all the negative from 1 to 4.
Right, so it's going to accumulate more negative area, exactly right. So A of 2 will be larger, exactly right. And again, Ryan could alternatively give a very similar kind of decreasing, increasing argument if he chose to as well. So B, both are legit. So A of 2 is larger because, and again, there's different ways to put it. I'm just going to say less negative area is accumulated for -3 less than or equal to x less than or equal to 2 than -3 less than or equal to x less than or equal to 4. Okay? There's less negative area being accumulated. Okay, very good. All right, so letter C, where is A increasing justify? Okay, where is A increasing? So first of all, we got to think, okay, when is a function increasing? All right, so one way you can determine when a function is increasing is if you have the graph of the function, you just look where it goes up from left to right. Do we have the graph of A here? No, this is not the graph of A, it's the graph of lowercase f. Okay. So Tyler, how can we use this graph of lowercase f to determine where is A increasing? Yes. So, and again, watch all those pronouns there, but basically you got the right idea, exactly right. So yeah, so where this is the derivative. So f is the derivative. So you can say something along the lines of this. A is, so in this specific case, by the way, Tyler, where is A going to be increasing? -3 to 1. So yeah, A is increasing for -3 less than or equal to x less than or equal to 1. All right, and it says the word justify, so you need to put a because. And again, just saying because f is positive on that interval, I don't think is quite enough, because you haven't connected f back to the original question A. Like you need to make that connection in the grader's mind that you're using f to describe A. You need to make the connection right here. And the easiest way to make the connection is just say because A prime of x, which is equal to f of x, okay, because A prime of x equal to f of x is positive on that interval. Okay? Just like in the past, if we were given a graph of f prime and asked to talk about f, we would say because f prime is positive on the interval. Here we have to make that additional connection. Okay? Alright, cool. Letter D. So does capital A have a relative minimum, relative maximum, or neither at x equals 1? Justify your answer. Alright, so here's x equals 1. Alright, that's for x equals 1 of f. Will A have a relative minimum, a relative maximum, or neither at x equals 1? Let's see here. Let's go to Jack. What do you think there? Okay, why do you say that A will have a relative maximum there?
Because f of x changes from positive to negative.
Beautiful. That's it. Exactly right. So we will have a relative maximum at x equals 1 because, and again here, I'm going to write A prime of x equal to f of x changes from positive, I know it was loud. Oh, it was a teacher? I should.
Sound like,
Go get him, Mr. Weird.
sound like a man's
That's right.
voice.
I can break up fights.
Someone yelling at
Throw some bows.
Get a compass.
Mr. Wood, you lift like every day. Of course.
Someone like, there are students in the past, they're like, Mr. Wood, you can't break up a fight, you're too fragile.
No, Mr. Wood, you work out every day.
And I was like, what's that supposed to mean? Anyway,
I see you,
Um,
I see you clean every time you're in the weight room.
that's right, I clean it up.
Major karate.
Oh, yeah.
So,
Major karate.
I'm not quite done talking about this one yet, though. Sorry, guys. So, does A have a relative minimum, relative maximum, or neither x equals 1? Justify your answer. Okay, so, again, that's your, like, justification there. What else do I want to say, though? Something about... Oh, why am I allowed to say that A prime of x equals f of x? What am I using when I say that A prime of x equals f of x there? When I take the derivative of that integral,
You're just gonna get f of x times x prime.
but what thing am I taking advantage of that I'm able to do that? Second fundamental theorem of calculus, exactly right. Remember, folks, right, when we take the derivative of a function, and it's a function defined as an integral, taking the derivative integral is the second fundamental theorem of calculus. You plug the x in where the t is, right, and then multiply by the derivative of x, which is just 1, so it's just f of x, and then you subtract the lower limit, negative 3 plugged in, times the derivative of negative 3 is 0, that's why the lower limit disappears, and it's just a prime of x is equal to f of x. That's the second fundamental theorem of calculus we're applying there, okay, to get that. Exactly right, Ty? Yeah. Okay, so that's the idea. Yeah, Brandon?
Which is better to say, like the actual application of it, or just saying using the fundamental theorem of calculus, f of x changes from positive to negative?
I mean, I think this is sufficient, like right here, what I just said. You don't have to say because it's the second fundamental theorem. I think it's safe to just say that, though. Say.
It might ask if they use fundamental theorem.
No, but just like, I just wanted to kind of review that idea that that's what allows us to do that, because you will see problems where, I mean, you could potentially see a problem defining an integral like this, and then just find what is a prime of x, and you have to come up with a function which is be then f of x. Yes. For C, yes?
Wait, why is
Why is it positive? It's from negative 3 to positive 1. Okay, why is A increasing there? Okay, so what do we normally use to determine whether a function is increasing? What do we look at? The first derivative, right? Okay, so let's imagine here. Here's my function A. It's this integral. But if I take the derivative of A prime, the derivative of the integral, by the second fundamental theorem of calculus, it's just going to end up being f of x. Where's f of x? Right here. So this thing, even though it's called lowercase f, we really could x that out and really say it's the graph of a prime of x, because in this case it turns out to be the exact same thing. Even though this thing has a lower limit of negative 3, doesn't matter. If I take the derivative of both sides here, that'll be a prime, that'll be just f of x. The lower limit disappears because you're taking the derivative of a number. So this is a graph of a prime. If I want to know when a is increasing, I want to know when a prime is what? Positive. Where is a prime positive? From negative 3 to 1. It's above the x-axis. So that's how we know that. Okay? Same argument then for why do we know that A has a relative minimum, relative maximum. Well, there's our critical point, because that's A prime, and then change from positive to negative. Okay? Did you have a question, Ryan? Okay, cool. All right, let's flip it over. All right, so I would actually, let's read through it here. So a particle moves along a coordinate axis. Its position at time t in seconds is s of t equals, and then we have an integral here from 3 to t of f of x dx feet, where the graph of f is shown right here, okay, and it's a line segment and a semicircle, so that's supposed to be a semicircle right there. Okay, so this is f of x, okay. I want you to tell me the particle's position at time t equals 0, so go ahead and find that particle's position at time t equals 0, please. Give that a shot. Okay, on your own there. And again, s of t is the integral from 3 to t of f of x dx. So it means here for s of 0, it's going to be the integral from 3 to 0 of f of x.
Blank feet, but then it's like from where?
I don't think so, because we're about to find out where the particle starts, because we're finding time t equals 0, what the position is.
It's just like the x-axis.
It's along a coordinate axis, so it could be the y-axis or the x-axis. We're not told which one it is. So go ahead and answer that problem right there. What is the integral from 3 to 0 here?
Good.
How to get to
You're saying which one, you're gonna try this over here, right? What's the base 1, so you're saying that's your base 1? Right, exactly, have your parallel sides there, yeah, so I just adjust
What?
that there real quick.
What?
I was trying to remember the position.
Oh, that's your answer, okay, so let's see how to get there. You made like a rectangle and a triangle? Okay, that's fine, so what the area is rectangle? 6, and what's the area of this triangle? We have, so 6 plus we have.
Yes.
You don't have to build it.
Not really.
Don't forget, we can't put units here too, we have a unit for the position. Yes, yeah, and it doesn't say include units, but let's do it for good thing. Good, yes, good. Yes, excellent, very good. Yes, good, yes, very good,
Okay.
Okay. It's a negative sign.
Okay, good. I couldn't tell. Okay, yes, very good. Yes. Okay. All right. So let's pause real quick here and take a look. So let me go to Emma. Emma, what'd you get for letter A? You got what? Sorry. Negative 7.5. Okay. Negative 7.5 feet. Okay. So why is it negative though, Emma? If I do this is an area. An area should never be negative, right? Right. We are integrating backwards here, folks. Right. We are integrating from the right to the left. So that means this. If you integrate from right to left, that means the integral will be the opposite of going from left to right. So integrating left to right, absolutely, we get a positive 7.5 area here. Integrating right to left will yield, in this case, a negative 7.5 feet. Okay, so exactly right, though, negative 7.5 feet. Excellent work. All right, let's look at letter B. All right, what is the particle's position at time t equals 3? It's got to be 0, right? S of 3 is equal to the integral from 3. The 3 is replacing the t, right? That t right there is 3, so we integrate to 3. Well, the integral from 3 to 3 of anything is 0, so 0 feet. Okay. All right, let's look at what the particle's speed is at time t equals 4. Speed is time t equals 4. So, ideas here? How can we find the speed at time t equals 4? Yeah, Connor?
Well, you can kind of take the derivative of x, but, well, you can't take the derivative, you just have to use...
What? Yeah, no, we can take the derivative here. What's the thing we're taking the derivative of, though?
The way I thought of it, like, I knew you were looking at the slope of the line at that point.
this right here is the graph of the slopes, you're saying? Or you want to find the slope at time t equals 4?
Find the slope, find the speed.
Okay, so yes, we do want to find the slope of something, but it's not the slope of this function.
It's the slope of the
It's the slope of s that we want. Okay, speed is related to velocity. Right? Speed and velocity very similar, right? Velocity you can get in miles per hour, whatever. Speed you can have in miles per hour. Velocity can be meters per second. Speed can be meters per second. Okay? So velocity and speed are kind of like the same, almost the same concept, except for one catch, right? So given the position, and if I want to find speed, what should I do with this position?
double derivative.
Just the first derivative. Second derivative of a position gives me what?
Next, about acceleration.
All right, answer my question, though. Acceleration, okay, that's right. So then we want the velocity, so I take the derivative of position. All right, so I want to find s prime of 4, which is f of 4, right? S prime is equal to s prime of x, or I should really say s prime of t, sorry. S prime of t is equal to f of t. Right? So that's the velocity.
So the function that we have right now is basically
This essentially is the velocity, yes.
okay.
So, and I want to evaluate it at 4. So what is the value at 4?
It would just be
Negative
negative.
1, okay. Negative 1, what would our units be?
Feet per second.
Feet per second. Okay, now, that's the velocity, is negative 1. What is the speed? 1. 1. Okay? Remember that speed is equal to the absolute value of the velocity. So, the speed is 1 foot per second. Speed does not have a direction to it. If I drive forwards 5 miles per hour, I say my speed is 5 miles per hour. If I go in reverse 5 miles per hour, I still say my speed is 5 miles per hour, right? The police officer will still pull you over if you drive forward at 50 miles per hour in a 25 mile per hour zone, or if you drive backwards at 50 miles per hour in a 25 mile per hour zone. They'll probably give you additional citations if you're doing it backwards. You know, it's like bonus time. But for velocity, there is a difference, right? If I drive forward at a rate of 5 miles per hour, then it's a positive 5 miles per hour. If I drive backwards, then it's considered a negative 5 miles per hour, or, you know, whatever the context might be. One direction will be positive, one direction will be negative. One direction. Okay, sorry. Letter D, approximately when is the acceleration of the particle positive? All right, so now we're talking about the double derivative, right, Connor? Because we're talking about acceleration. So let's get someone else here. So let's see here. So Donovan, ideas here. We want to know when is the acceleration of the particle positive. So ideas on this? When the graph is, yeah, very good, increasing. Exactly, because again, this is like the velocity. To find when the acceleration is bless you. If the acceleration is positive, that means the velocity will be increasing. So, what's the interval here then?
Would it be from 4 to 7?
4 to 7, yeah.
Is 5 not a matter that changes its direction?
I think we'll be okay there because the velocity, because it's increasing immediately to the left and immediately to the right of it. So I think we should still be okay there. So 4 less than or equal to t less than or equal to 7 because f of t, or I guess it's f of t at this point, f of t is increasing. Actually, I should say it this way. Hang on. How do I want to write this? Because
I heard a lot for that.
all right. 4 less than or equal to t less than or equal to 7, starting over again, because s prime of t equal to f of t is increasing on the interval, and I think that is enough. I don't think you need to do the further interpretation that because s prime is increasing, therefore s prime prime or f prime of t or a of t will be increasing, or is positive on the interval. So I think that's enough. It's sufficient. I think that is sufficient. All right. Last one here. At what time during the first 7 seconds, so basically for our graph there, at what time during the first 7 seconds does the position have its smallest value justify your answer? So I'll let you guys sit and just think about that for right now, okay? So take 30 seconds or so and think about that. Again, we're given the graph of the velocity here, the derivative of the position, essentially. At what time during the first 7 seconds does the position have its smallest value? So I'm not asking you to actually find that value, but just at what time do you expect the position to have its smallest value, and be prepared to justify your answer there. Okay, I'll kind of come around and see how Yes.
I don't want to write it down because I'm not sure it's right, but
you don't write it down.
so the position is the integral of this graph from 3 to t. So it would be 5 from 3 to t would just be negative.
Okay, I see what you're saying. Yes, there's a negative area there. Yep.
Yeah. And then
If you were to go beyond 5.
this is all negative 2. This is all negative. Oh, so yeah, we just do 5 because beyond 5 we're starting to get positive.
I mean,
all this
You
absolutely.
decrease the 5 and then you increase from 5 to whatever is small.
Yep. So I mean that's correct what you said. Yes.
Okay.
From at 5 you have decreased from 3. Exactly right. Not sure. Not sure. You had to guess.
Convert from
You want to write it down. I see the 5. Okay.
Doesn't have no?
Because you can write from left to right, or right to left. What do you think? Why do you think that? Because that value. Okay. Okay, why?
5.
Here, so that's pretty low. But if you think about what you're not doing, we animate from 3 back to 0. That's a lower value. It's not a high spot.
Joey. Oh my god. You're thing I thought it was real. What? Because my... Wait, who are you talking to? Because if I start to grow my hair long, it gets gross.
No, it's already gross. Your hair's never been.
It has. And it gets kind of curly.
I want it to get long.
I would eventually have hair kind of
Let
like
it get long. Don't grow it. Don't cut it until next.
So can you tell me what's unnecessary in my dissertation? That looks like a big paragraph.
All right, we'll talk here about it. Just a second. Let me go through the answer. Get this. So okay, so
From now on, just grow.
So I saw two major answers here, I would say. Mostly two answers here, okay? The two answers were at time t equals 5, but I also saw time t equals 0. Okay. Now, the magic of this problem is that we actually can figure out both. In fact, we've already figured out one of those values, didn't we? The position at time t equals 5, actually, sorry, we figured out the position at time t equals 0 in an earlier section, right? What did we figure out the position to be at time t equals 0? Negative 7.5 or negative 15 halves, that's right. Okay, and we can figure out the position at 5 as well. To figure out the position at 5, right, it's like plugging t equals 5 into our integral here. So we integrate from 3 to what? If we want to find the position at 5, that would be s of 5. So that would equal the integral from 3 to, what would be here? 5. Okay, the integral from 3 to 5 is a, what kind of shape? Half a circle, semicircle, right? Okay, so with a radius of 1. So pi r squared is the radius, or sorry, pi r squared is the area, so 1/2 pi r squared for half a circle. So r is 1, so it's 1/2 pi times 1 squared, so 1/2 pi. Negative 1/2 pi, right, because it's below the x-axis. So, which one gives us the smallest value? T equals 0 does. T equals 0 is the smallest value here, okay? And the reason for that, so again, I see a lot of you guys what you were thinking. You looked at your picture here and you said to yourself, all right, the only negative area that we have is this piece below the x-axis. And you're right, this is the only negative area. So at time t equals 5, right, that would be kind of like the lowest point. And we're integrating from 3 to 5. But you have to be careful here. Because yes, we're integrating from 3 to 5, so that does yield a negative area. But because we're integrating from 3, when we integrate from 3 back to 0, even though this looks positive because it's above the x-axis, since we're going the wrong direction, it really ends up being negative. And so that's why that 0 yields that negative value, the lowest negative value, in fact. Okay, so t equals 0, okay, is the location of the absolute minimum. All right, you want me to say that again, Connor?
Oh my god, but
Oh my god.
But wouldn't the t equals 5, wouldn't it also include the negative 7.5? Wouldn't it be like negative 1/2 pi?
Where are we integrating from? 3.
Once you get to
No, boy.
No, but I thought at 0 it's 7.5 and then
Why would you add the negative 7.5 to the negative?
That's all I just had.
What are we integrating from? 3. So we're integrating from 3. So when we, at 3, remember we said the position at 3 is 0. So when I integrate from 3 out to 5, I am adding on to that a negative, 1/2 pi or whatever. And so that's why the value at t equals 5, the value is only negative 1/2 pi. Integrating backwards from 3 back to 0, the original time position 0 there, that would then give us the negative 7.5, which is a larger value there. Yeah. Okay. So f is positive from left to right, but since we're going backwards, if you go backwards on an increasing interval, you're going backwards. That's a decreasing interval. Then you're going down. So anyway, t equals 0 is the absolute minimum. Okay. Essentially, here that's what we're being asked, right? Smallest value, or where at what time does it have its smallest value? We're asked about the location of the absolute minimum here. So to kind of consider this, we really need to consider all of our endpoints. Okay. We kind of already showed that work here, all right? T equals 0 is negative 7.5, t equals 5 is negative 1/2. So we included those two. We can also say that, at time t equals 3, which is a critical point, then a of 3 is equal to 0. We said that. That's equal to a of 5. Sorry, that's equal to a of 0. And there's one more point we have to check. We should also check what other point here. For absolute extrema, we checked the critical points. So we checked at time t equals 3 and time t equals 5. What else we need to check for absolute extrema? The endpoints. Well, I checked 0, right here, a of 0. I also checked a of 7, though, just to make sure. So a of 7 is, oh gosh, I didn't do that. So it's going to be what? Negative, nope. A of 7 is going to be the integral from 3 to 7. So it'll be negative 1/2 pi plus this area of this triangle here. So it's 1/2 times 2 times 1. So it's negative 1/2 pi plus 1. And so clearly the winner here is that negative 7.5. Okay? the areas? Yes, I think, yes. So I'll come to that point. So T equals 0 is location of absolute minimum because A of 0 yields the lowest value. I think this is maybe the most efficient answer, I would say, potentially. Less writing. I feel like there's a whole lot, like I can see you have a whole lot more written there. And that's fine, absolutely.
Kind of figure out how to put it just because it's a little more complicated.
Exactly. Yeah, and that's why I think this is maybe nicer because you're hitting all the things you need to hit for absolute extrema. You check the endpoints, you check the critical points, you check to see which one, because you can find the value here, I would say that. When in situations where you maybe won't be able to find the exact value, but you can still use that area idea, your answer would be the way you want to go, for sure. Yep.
Could you just explain that the velocity will never allow it to be the position to be less than where it begins at? Because it's going to be increasing and then decrease a little bit, but not enough.
I think, again, the idea is like the little bit part, like how much is a little bit, you don't really know. In this case, though, since we can actually find those areas, we use those exact areas and then show it precisely. So I think, again, there will be situations, Christian, where, yes, it'll be more nebulous. You won't know the exact value, to kind of say, well, this region is clearly smaller than that other region, so that kind of thing. So, yes, that'll be a sufficient answer in those cases. I would say this is a better way to go. Would you lose points potentially in a situation like that? That I can't really say. Depends on the grader.